Okay, so I'm going to put off linearization for a minute. I got the linearization behind that board actually, and the trim chart. I wanted to show you that video, but let's do the dimensional derivative really quick, just to review. We're just going to review some stuff from before. So if I get CMQ from the table, how do I get the moment derivative MQ? And if you remember, there's 6 equations, and you need to know that we're always solving for the variable dot. So in the Q equation, we would be solving for Q dot. So we'd have something like for Q dot, and then it would be equal to 1 over IY, because we always normalize by the moment of inertia by the mass. And then it would be partial M over all the partial derivatives, and I'm using Q, so we'll have partial M over partial Q. And you can use either the little q or the big Q. This one's linearized, that's not linearized, but they're basically the same variable when they're changing. So partial M over partial Q, and we have to evaluate that, of course, at the steady state condition, and then that would be times delta Q, or times Q. And then there would be the rest of the terms. You know, we look at these, there's motion variables, all the rest of it. But this one here is what we have called the stability derivative. The stability derivative is this guy right here, and we can see it's going to have dimensions, because this guy on the left is feet per second squared. So if I've got feet per second over here on Q, or no, I'm sorry, this is going to be, Q is radians per second squared. So if I get radians per second over here, then that means that this dimensional derivative has to be 1 over seconds. So that radians per second squared comes out left and right for all the terms. So that's a dimensional derivative, and we call it MQ, as units of 1 over second, like so. And in the table, I'll look up CMQ, right? I'll look that up in the table. So how do I get MQ from CMQ? You have to know how to do this for all the stability derivatives. You have to know their name, and you have to know the physical description. So the name of this is pitch damping. And why would it be called pitch damping? Because whenever I have a pitch moment, or a pitching rate, a Q, whenever I have a Q, you see how the tail is wagging in the breeze back there? So the longer the tail, the more it would be wagging, right? So it's generating an angle of attack that's opposing the motion. Whenever I go like this, it's generating an angle of attack that wants to counter that motion. Otherwise, it would spin out of control. So the pitch damping derivative is always negative. And whenever I have a positive Q, again, if I stick my right hand down the right wing, this is positive Q, I want a negative moment. So my pitch damping moment is negative. So that kind of summarizes what I expect you to know from all these stability derivatives. This is pitch damping. Its sign is negative for stability, right? And physics says that it will be negative whenever I have a positive Q. The moment from the tail moving, or the Q from the tail, is going to be negative. And you can convince yourself that's the case, even if it was a canard, you can convince yourself that would still be the case. There would always be an opposing moment. So this is pitch damping. It's going to be equal to 1 over IY times the partial of the moment. Now I know the moment is Q bar SC C sub M. If I non-dimensionalize it, over partial Q evaluated at the 1 condition. So Q bar is 1/2 rho V squared. That's the wing area. C or C bar is the wing chord. And that's your dimensionless constant for the coefficient of moment. So this takes all the dimensions out of it. Pounds per square feet, foot pounds. I got foot pounds here, so there's no moment on this. Foot pounds divided by I sub y will give you the correct units. So if I were to do this guy, this would be, I'm going to take out the SC, so we'll have, let's see, over partial Q, Q bar, SC bar over IY. And now I've got partial M, partial C sub M over partial Q. But I'm going to have units on that, yeah? because Q has units of radians per second. So that's not allowed. So I have to have partial CM over partial Q hat. Well, Q hat's going to be dimensionless. Then I have to take partial Q hat over partial Q to give me, by the chain rule, that gives me back what I had before. I just need to know what Q hat is. Well, you can kind of guess by now. Q hat is going to be equal to wing chord over twice the steady state velocity, VT1. So does that give you the right units for Q hat? C over 2 VT, feet per second, seconds in the numerator. I think that's going to work. Yes? Feet per second. Well, let's see what happens. So this is going to be equal then to be equal to Q S. I'm going to have C squared, QSC squared over 2 IY VT1 times partial CM partial Q hat, which we'll call CM Q. And there you have it. Okay. What's the secret handshake? The secret handshake is that CMQ is really CM Q hat. There's no dimensions on it. So you have to remember the secret handshake is I non-dimensionalized this, and I made all these terms appear. And there's a table in Nelson that you can maybe print out, put in your notes for the next test or for the final exam. And it's got all these formulas in it in one table. So what I'd like you to do this week, I would like you to do, how about C, how about drag? You do drag due to velocity, du. You do du. I'll get you started. So that's going to be 1 over the mass times partial drag over partial u evaluated at steady state condition. I'll get you started. So that's going to give you the right dimensions for it, normalized by the mass. And then if we were to put that into the formula for u dot, then you'd have partial d partial u times u over here. So this, you'd see that this would have units of 1 per second. The du would have units of 1 per second also. So you do this for your readiness check. That's going to be worth 10 points. Okay. 10 points on your readiness check that's due this week. Questions on that?